So next we're going to be covering Markov decision processes, and you should all have the Markov decision processes, a copy of these notes in front of you. So now we've got the two basic ingredients that we want to now combine. We've got dynamic programming, this idea of solving an optimization from back to front, okay? And we've looked at Markov chains, the idea of these kind of processes where you have the state and then some random outcome determines the next state, all right? So we basically want to combine these two things together, all right? So that's what we're going to do in this section, all right? So as in section 1, we're going to again assume that time is discrete, okay? And we're going to consider states x in some set of states script x, all right? And you're going to be allowed to take actions a in some set script a of t, okay? And given the state that you're in and the action that you take and also the time, you're going to receive some reward, okay? However, before, the evolution of this process x was deterministic. Given the state and the action that you chose, the place that you ended up next was for certain. All right? Now, the plant equation is slightly different. In fact, it's going to evolve in a random way. Okay? So, specifically, states are going to evolve according to functions. Oh, and typo. Told you there'd be typos. That should be capital F, if we're going to use capital F there. F of t of x of a, and then some uniform 0, 1 random variable is going to determine the next state x. All right? So we've got the next state that I end up at, x of t, is a function of my current state, and the action that I take, okay, just like before for the dynamic program, but like the Markov chain, there's some dice throw, or uniform 0, 1 random variable, that determines my next state. All right? So we've got the three components now that decide where you're going to end up at next. Okay? You've got your current state, the action that you choose, and then some randomness. Okay? So in a dynamic program, we just considered the state and the action. In the Markov chain, we considered the state and then some uniform randomness. And now we're considering all three of those things together. Okay? Does that make sense? Is that okay? And again, this is called the plant equation. I've written the uniform random variable here with the semicolon. I'm often going to suppress the uniform random variable when I write down the plant equation. Okay? So it should be understood that if I'm saying it's a Markov decision process and I don't write the u of t in it, that it's still random. Okay? We could also think of this being this function being a random variable. That's another way of thinking about it. Okay? For simplicity, just think that that u of t should be there, but I haven't been bothered to write it because I can't be bothered to write it all the time. Okay? Right. Okay, so one way of thinking about this would again be my board game example. So just draw a picture again. So remember I had my board game example. Okay, and there's some ladders, I don't know, some ladders and some snakes. Okay, doesn't really matter. Okay, now let's suppose that you're allowed to play the game. Okay, start from the start here to the finish here. Okay, but now you've got two counters. You've got 1, you've got 2. All right. and you're allowed, after you, let's say you throw the dice, okay, and you're allowed to decide which counter you're going to play. All right? So you decide which counter you're going to play, then you throw the dice. And now you've got a decision to make as well. All right? So a lot of board games that are like that. So before, everything was just completely random. We had no choice. And now, if you compare it with a game like this, where we've got multiple counters, for example, the game of Ludo is like this. I don't know if you've played Ludo before. That's a similar game where there's randomness, but you've got multiple counters to choose between as to which to move. Okay? Now we're in a setting where we've got a Markov decision process, because we've got a random dice to throw. Our state is the position of the two counters together. Okay? And we're trying to maximize an objective, let's say trying to minimize the time to finish the game, to get one of the counters at the finish. All right? So that would exactly be a Markov decision process. Okay? So again, like with the dynamic program, we had the idea of a policy. A policy chooses an action, pi of t, at each time t. Okay? And the information that you're allowed, so this is important, the information that you're allowed to use is the sets of past states and past actions that you've chosen. Okay? So you don't know the outcome of the next coin throw necessarily. Okay? You get to make your decision before you throw the dice, sorry. Okay? You can change that if you want. That's still acceptable. But for now, we'll work with it that way. Right? So a policy chooses an action in a sensible way. You kind of know what's happened up until that point, and then you make a decision when you're at that point. And you can use all the information of the past up until then to make your decision. Okay? Okay? So a policy, a plant equation, and the resulting sequence of states and rewards that we get from this is called a Markov decision process. Okay? So it's a Markov chain for where you make decisions, essentially. Right? And the objective is very similar to what we had before. We want to maximize the sum of rewards. Okay? So here, if we're given an initial state x0, a Markov decision problem, okay, is the following optimization, where we maximize, okay, the sum of the rewards, R of t, of the states and actions, sum from time little t to capital T, and then the reward you get at the last time. Okay, so we sum up all the rewards and look at the expected value of those. Okay? So the expected reward, we're looking at the expected reward of some policy pi. Okay? And we want to maximize that over all the policies that I can take. All right? And here, Wx is the optimal reward. Okay? It's sometimes called the value function. Right? Again, I'm going to let r tau x tau of pi be exactly the same expression as here, but where the sum doesn't start from 0, but starts from tau. All right? So just the same as before, r of tau is going to be this function, but with the sum starting from tau and not from 0 here. Okay? And w tau is going to be the maximization of that term. Okay? So where we just look at the rewards from now until the end of time. Okay? Right, that all sounds very abstract. So we've kind of positioned this in terms of our Markov processes or Markov chains view. So we covered Markov chains. I said, how do we change the problem slightly to make it Markov decision process? Let's look at how we can look at the dynamic programming perspective and see how that looks as a Markov decision process. So I'm going to write down an example quickly, just here in this space. So let's consider the following. So we have, I'm going to draw a tree. Okay. And each of the nodes of this tree, or leaves, or whatever, I'm going to draw a reward. Okay. Minus 10 there. Three. Okay. And then a bit like before, I've got a choice. I can go left or right. So I can go left and get a reward of 1, or I can go right and I can get a reward of 0. Okay, and let's say the reward from that node is 2. Okay, same here. I can go left and get a reward of 0, or I can choose to go right and I can get a reward of 1. And let's say the reward of that node is 3. Okay. Now, here, I can go left, I can get a reward of minus 10, or I can go right, and two things can happen. Let's say with probability 2/3, I end up at the 3, with probability 1/3, I end up at 0. Okay? Then I'm going to assume we're here at the root node. Okay, I can either go left or I can go right. And if I go right, two things can happen. So let's say with probability 1/2, I end up at this node, which I'll write reward 1 on it. And with probability 1/2, I end up over here. Okay. So this now is exactly the same as that tree example before, but now I've got some randomness in it. Okay? And I'm going to solve it in exactly the same way as before, but I'm going to account for the randomness. Okay? So what would I do in order to solve this? I was going to apply the same idea as I was applying from the dynamic programming setting. What would I do to this tree? So where would I start? Would I start here and exhaustively look through all of the roots, or what would I do if I was going to apply that kind of dynamic programming paradigm? Yeah, so we start at the leaves. So I'd start at this part. Okay. And it's rewards, so I'm maximizing rewards. This is I get £2, that's I get nothing. Okay. So here, do I want to go left or right? Left. And the total reward I get is, sorry? 3, yeah? Okay, this one. So this is just the same as before. I can go left and get £0, I can go right and get £1. So what do I want to do? Right, and the total reward I'm going to get at this point, sum of these two is, sorry? 4, okay? This guy. I can go left and I can get minus 10, so I have to give someone £10. Or I can go right. 1/3 of the time I get nothing, and 2/3 of the time I get 3. Okay? So what do I want to do? Left or right? Right. Right, yeah? What's my expected reward? 2, and then add to the 1, in total 3. Okay? So the reward is 3, which is equal to 1 plus 3 times 2/3. Okay? So I get 1 from being here, and then I get nothing if this happens, or I get 2/3 times 3, which is 2. Okay? All right? Right, so now I'm here. I go left and I get a reward of 3, or I can go right. Half of the time I'm going to get 4, and half of the time I'm going to get 3. So if I wanted to maximize my expected reward, okay, what would I do, left or right? Right, yeah, because I'm going to get a higher expected value from this decision, okay? So the answer is going to be 3.5, okay? So the point I'm trying to put across is really not any more difficult than the dynamic programming case. We just need to take some expectations at certain points, okay? So let's write that down. So the idea is the same as dynamic programming, but you need to take expectations. Right? Right, so what I explained is all very well and good if we just want to solve things on trees, but that doesn't sound very interesting to spend all, I mean, although ultimately we are spending all our time solving things on trees, it's kind of nice to consider things as examples, which actually, you know, might be somehow financial, because we've got a finance course to teach. Oh, yeah, one thing. Bellman's equation. That's an exercise for you guys. All right? So I want you to look at the way we proved Bellman's equation for dynamic programming and just think how we might apply this in the Markov decision processes case. Okay? You've learned enough stuff to be able to do that. Okay? So it's a good one for you to try out, and obviously we'll go through the proof of that in the tutorial, okay?